So I'm Jonny. I long ago went to a school that I won't name for fear of my own safety, but it's another Bay Area school. I was a mechanical engineer there. I've met a lot of mechanical engineers today, so I'm really excited to see that tradition lives on. And I've done a lot of stuff in space in my career. Early on, when I was in undergrad, I actually interned at SpaceX. In the very early days of SpaceX, 2003 and 4, I was one of 4 people in Texas at that time in SpaceX, so that was literally the Wild West. I also got some really unique opportunities to work at other very important startups along the way in what has become kind of the new space revolution. So I was early at a company called Skybox Imaging, which many of the younger folks in the crowd may not even remember, but this was the first venture-backed sort of new space satellite company founded in 2009. We went on had a really fantastic journey there where we built and launched 21 high-resolution imaging satellites, ended up getting acquired by Google, and then later sold again by Google. And then did a number of other things in my career, including some time in autonomous vehicles, as well as advising on a number of things in space like MethaneSat, which is a global methane emissions monitoring system that launched a couple of years ago. And so I've gotten to see and do a lot of different things, much of which has now culminated in what we're doing at Muon Space. So I'm really excited to kind of tell y'all a little bit more about that. I'm actually going to see if I can grab one of these microphones so I'm not leaning over. Test, test. Does that work? Okay. That's better. I think Muon Space is about 4.5 years old. We were founded in 2021. We're about 175 people. We're right in the Bay Area, down in Mountain View on the peninsula, so another local company. We're growing very fast, venture-backed. We've raised 3 rounds so far. We have launched 4 satellites to space, 4 working satellites to space to date. And there's a ton of exciting stuff coming up on the roadmap. So I have some slides I'm going to go through just to kind of frame a little bit first about how I see the overall landscape in space right now, and then how I kind of see Muon fitting into that. And then I have a couple of examples of some of the work that we're doing that I think will be exciting for people. And I'm going to try and leave enough time for questions. I actually don't know exactly how much time I have because we're a little bit late, so somebody will have to keep me honest, and I'll try and get through the slides as quick as possible. I think as can be seen from events like this, space is very hot right now. We all got to see the pretty awesome Starship launch a week or so ago, and there's just a ton going on. It's a very hot topic across all elements of society. Investors are interested. There's a lot of money flowing into it, and so it's this really compelling, exciting time. Even in my career, I've seen that kind of excitement level or interest level rise and wane, and I think we really are on an upslope right now. And it's been changing really fast. I think that's a really important consideration. I look back to the time we spent at Skybox, which was a little bit more than a decade ago, and we were flying to southeast Russia to launch satellites off converted Russian ICBMs. And the cost to do that was something like 10 times the cost it is for us to launch satellites with SpaceX today. So you think about how much has changed in what's a little bit more than a decade, even from the basic perspective of access to space, and it really dramatically transforms how you think about what is possible to do in space. And I made this plot a couple of years ago. I really like this plot. It's actually now out of date, and it's probably, the numbers are probably even higher now. But this is a plot of the number of satellites in low Earth orbit going back, about 20 years, not quite 20 years. And there's a couple of things that you see on here that I think are really interesting. First of all, if you go back further, the number's flat. It was actually flat kind of into the early 2010s, and then it started rising on this kind of 5-year doubling slope right around the time that we founded Skybox, and that was kind of what I would consider sort of the new wave, or the first wave of this new space thing. What's really interesting is there was an inflection point again around 2020, and you now see that the number of satellites in LEO is doubling about every 18 months, and doubling every 18 months is Moore's Law, and we've seen what Moore's Law has done to the computing industry, and so you can imagine, what this type of dynamic can do in terms of a feedback loop for an industry and driving it forward. And I think we're just at the very earliest stages of that. I mean, obviously a lot of this is being driven by things like Starlink getting launched, but that same capability to put things in space at lower cost, faster, and higher volumes is going to affect everything we think about in terms of how we do stuff in space. And so, you know, we have this ability now to do things faster, better, cheaper. The question is, to what end? It's wonderful to be putting a bunch of mass in space. It's wonderful to be watching rockets. I love rockets. They're really cool. But like, what are we really trying to accomplish? And so I gave a talk. Sorry for the reference here. Many of y'all are probably too young to know this reference. During the Clinton campaign in the 90s, Jim Carville came up with this phrase for the Clinton campaign, which was, "It's the economy, stupid," and it became a very well-known, iconic political mantra. So for us, we like to think about it's the mission, stupid, and it's really not about the rockets and the fire or even the hardware, but it's like, what are we using this capability to solve? What problems are we solving for real people in real ways on Earth? And I love this picture. This is Apple's SOS system, emergency SOS satellite system, and a bunch of Skybox alumni were actually the founding team at Apple that built this product. And the thing that's so compelling about it to me is that for any of us with an iPhone, if we're out in the woods and we need help, we'll pull up our iPhone and use the service without really even thinking about the fact that it has something to do with space or its satellites. And I think many people use it never knowing that. So it's having this very profound impact on a lot of people's lives in a way that's totally transparent, is very impactful, and is really fundamentally enabled by a lot of these things that have been happening in space for the last 10 years. And so what we're trying to build at Muon, we think about as sort of a mission foundry. It is, our model is not that we're going to own every mission, it's not that we're going to solve every problem, but we want to enable that for many different types of partners and customers across a wide variety of organizations, companies, institutions, and really try and do that on a common platform. One of the problems today still with space is that if you try and do something new in space, it's still a very hard process. You have to develop hardware, you have to develop software, you have to have operations, you have to have a ground network. In many cases, you're developing a cutting-edge electronics package to do the data communication or the remote sensing. And we're now at a place where there's so much lower barrier to entry in many ways, things like the cost of launch, the access, the amount of launch that's happening. What we need to do is we need to lower the rest of the barriers to entry so that we can solve many, many more problems in space. And so the way that we kind of approach that problem at Muon is by partnering with entities that have a very particular problem they need solving, that is addressable in some way with a constellation of satellites in space, and then working, kind of arm in arm with them from cradle to grave to develop a solution to that. But really by leveraging a bunch of common building blocks that we've developed in a platform that enable us to do it quickly, economically, and scalably. And so we like to say, we design, build, and operate satellites for customers addressing some of Earth's biggest problems. This is a cool picture of our third satellite that was launched, getting integrated about 6 months ago in our clean room in Mountain View. I'll talk more about this in a little bit, but this is the first of what we call our FireSat constellation. So what you're seeing here is a multispectral infrared payload getting lowered down onto the spacecraft bus. That's satellites now in space producing data, and I'll show some of that later. And so when we engage with a partner or a customer, we like to think about three relatively simple questions. This may be obvious, but many times with technology-focused companies, I think these questions don't get asked early and often enough. The first is, what is the problem that we're actually trying to solve? It's not what is the technology, what is the capability, it's anything else, but ultimately, what is the problem we're trying to solve? The second one is, who cares? And the third one is, given who cares and what the problem is, what are some things we could actually do to solve that problem for that person? And I have in the backdrop here, again, a picture of wildfire. Well, in California, we all see very frequently how big of a problem wildfire has become. And one of the missions we're most excited about is FireSat. And again, I'm going to talk a little bit more about it in a second, but it really grew out of us working with a set of partners trying to deeply answer these questions. And the way that we go about that is we engage in something called formulation. This actually came out of, this was a concept that came out. It's an old concept in space, but it was really honed at JPL in something called the Innovation Foundry at JPL. And you can think about this as a very rapid feedback-rich iteration around a problem statement or a mission need that's done cross-disciplinary, in a very cross-disciplinary way. We have scientists involved, we have engineers involved, we have business people involved, and we have our customer involved. And we find that this process is often, A, not done well or not done at all, many times when somebody's trying to deploy something new to space. And B, it's really critical to do this well early in the process to get a good outcome. If you really want a solution that is going to solve the ultimate problem, going through this process early and often is really important. And we've built up a bunch of technical tooling, around this to make it a more modern, more scalable process. An example of that is our simulation environment. So this is a very high fidelity physics simulation that we've built for modeling everything from, you can think about power, thermal, attitude control, our communications network to satellites. In many cases, the way that an instrument or a payload is collecting photons and how all those things integrate together, so that we can, in a digital space, long before we've cut metal or had to build anything, turn knobs and see how we get the most out of a system and how we try and get something that is optimized not only for a performance requirement, but also the time it's going to take to get into orbit, the number of satellites we can put in orbit, the cost that it's going to be to do that. And so this is a really powerful tool that we've built that enables this approach. This is some other cool videos just showing various ways that we use the tool. And some more. I'm going to keep going so I don't waste time on this. The second thing that I think we've really tried to focus a lot on is it's one thing to build custom bespoke missions. The primes have been doing this for years. NASA's been doing this for years. The problem is, how do you do this efficiently? How do you do it in a way that isn't costing billions of dollars and taking a decade? And we really think the solution to this is a very modular, very flexible, and a very repurposable platform that spans the satellites that we're putting in space, the software running on them, and the network that we use to communicate with those satellites, so that when a customer comes to us with a problem, instead of doing a bunch of custom design and development on new hardware, new software, et cetera, we can often address that problem largely through some configuration and some tweaking at kind of the top level on top of the set of common building blocks that we have already developed and proven in space. You can think about this a little bit like, the analogy I like to use is like Lego Mindstorms. You can buy a Lego Mindstorms kit. I don't even know if it's still called Mindstorms. It used to be called Mindstorms, but it's a robotics kit. It comes with a bunch of parts, and you can build a robot or a dump truck or a conveyor belt or, I don't know what else, a bunch of different things with those same basic building blocks. And we see this as an analogy to the way that we need to very rapidly iterate, integrate, and deploy the right solutions to space to solve particular problems, but on a timeline and a cost that is not traditional in space. The satellites, just to give a little bit of sense for what we're building today, kind of come in two general flavors. We have about a 200 kilogram spacecraft we call the MuSat, and this is the primary one that we've launched to date. So we've launched 3 of these so far. They are, about 200 kilograms, can produce about 200 watts. This is what, for instance, our fire instrument is flying on. We're also developing a much larger spacecraft we call the XL, which is about 500 kilograms. One of the things I think we see as a trend, aside from the other things I showed in terms of the number of satellites in orbit, the cost coming down, is obviously things are getting bigger, Starship being the canonical example. But as we get things like Starship coming online, and not only the launch cadence getting higher, but the amount of mass you can put in orbit, it really starts to change how you think about what the unit economics in space are. So traditionally, we've been very focused on how do we pack as much into small spaces as possible. This was really a key insight in the early days of Skybox. We need to build small sats. We talked about small sats solving these problems. A lot of that was driven by the constraints of launch. As those launch constraints relax, it really changes how we think about building satellites. And we believe the future is actually going back to much bigger satellites, but doing it at sort of the costs and timelines that you might see traditionally for something like a CubeSat. And so our roadmap includes a lot of scaling into larger and more capable spacecraft, which then allows you to do things like collect more photons or give a payload more power or push more bits around a system, and that then gives a lot more capability. The other thing that I think is a little bit unique about us that I'm very excited about is, often with these missions, the spacecraft is necessary but not sufficient. The ground segment is necessary but not sufficient. Really, ultimately, what the moneymaker or the problem solver is the tip of the spear. It's the payload. It's what is moving the bits around. It is what is collecting the photons. And one of the other things we discovered early on with several of our missions is as we went through the formulation process, developed a concept for what really needed to get built to solve the problem, is that the first roadblock you run into is that payload does not exist. And so we've also, out of necessity, taken on developing some in-house capabilities on the payload side, which then allow us to fully vertically own and deploy a lot of these very, very, very high performance systems. Things like the infrared camera I'm going to talk more about on FireSat, as well as a bunch of radio frequency payloads we're developing for a number of customers that span both remote sensing and communications. And so I've kind of alluded to it a bunch, and I wanted to just spend a few more minutes talking about this because I think we see this as kind of a marquee example of the value of our approach, kind of this mission foundry, mission first approach, actually kind of being manifest in a problem that we can all relate to and are very excited about. So FireSat is a cross-organization partnership that we are one of the members of. It also includes a nonprofit called the Earthfire Alliance, which is a 501c3, so a U.S. nonprofit, whose mission is basically to transform the way that we manage wildfire in the landscape by providing land managers, first responders, operators, sort of a sea change and situational awareness around where fires are, how they're burning, how the landscape is affecting the risk associated with wildfires, and then obviously all of that against a backdrop of a changing climate. And so we've been working on this for about 4 years now. Other partners in this include some of the folks at Google.org and Google Research, as well as the Moore Foundation, which has a big initiative around wildfire. And the ultimate goal is to deploy a 50-satellite constellation that is very much targeted at this wildfire problem. And we spent hundreds of hours working with stakeholders across fire agencies, climate and fire modeling scientists, a bunch of the land managers, the folks that are responsible for doing things like forest management, to really understand, again, what the key problems were in the space and what you could do from a space-based remote sensing perspective to put a big dent in it. And what we arrived at is essentially this 50-satellite constellation, which will provide both things like fire managers like CAL FIRE, Cal OES, near real-time situational awareness on new fire starts, but also, and I think maybe more importantly, as a fire is burning and they're trying to manage it and provision resources, something like 20-minute updates through the entire life cycle of the fire at sort of a resolution and fidelity that has been completely unprecedented in the history of space systems. And so it's not just an incremental step in terms of their ability to understand what's happening and manage it. We think it's an order of magnitude or a couple of orders of magnitude improvement. And so we launched the first satellite, what we call Protoflight, in March. And I think this is a really good kind of case study of our approach. You know, the traditional way to solve this problem would have been to go through a formulation process, come up with a set of requirements, and then 10 years later start deploying the satellites. Once we knew what this system ultimately needed to look like, we went from that to having a first satellite in space that was demonstrating the data we'd collect in about 15 months. This is, completely unprecedented from the perspective of most large organizations that would be deploying satellites like this. And what that affords us to do is learn a lot very rapidly in ways that you can't do on the more traditional approach. And so The satellite's now been in space for about 4 months. It's producing data. We're learning a ton from the data. We're very happy to report that the data looks fantastic. But we're also getting to do a lot of things very early in the overall life cycle of this mission that normally you'd never get to do, like sharing data with the downstream users and customers that are ultimately going to be incorporating this into their operations. Typically, that wouldn't even start until many, many years later when the satellites are really getting deployed. And often that's the gating item. It's that getting data out the last mile to operators and first responders that prevents the uptake of these systems. And so we're really excited that this approach has not only allowed us to prove out the technology, which it's doing very effectively, but it's also allowing us to really get data in the hands of people that are ultimately going to be consuming it and learn from that process so we can incorporate that as we continue to scale it out. And I have a simulation here that I think just viscerally really shows the impact that a system like this can have. So this is a simulation of a fire propagating against the landscape kind of from above. And you can think about this upper left quadrant as temperature. So it's kind of like the thermal signature of a fire moving in the landscape. And then the bottom two panes here, we're simulating. There are existing satellites that are used for looking at fire. They're typically weather satellites that were designed for weather forecasting purposes and not really with fire in mind at all. And they all have significant significant constraints. And so this is two of the civil satellites that are currently being used for wildfire purposes. One's called VEERS. It's a polar orbiting set of instruments on our NOAA weather satellites. It updates about every 12 hours, and it has about a 400-meter resolution. The other one is GOES, which is a geosynchronous satellite also used for weather forecasting, which updates much more frequently, but the resolution's about 1 kilometer. In this case, for this simulation, the simulation doesn't even go 12 hours, so we just showed an update on VEERS, so you see something. But what you very clearly see is if you're on the ground trying to understand where is this fire, how hot is it, where is it moving, ideally catch it when it's small before it's gotten big and out of control. This satellite data is almost useless, and that's the recurring theme you hear when you talk to first responders. The upper right pane is a simulation of what the FireSat constellation will see. And again, if you kind of put yourself in the seat of somebody that's trying to make decisions about where do I put resources, is this on this side of the highway or that side of the highway, where should I evacuate houses, this is really a transformational view into what's happening on the ground. So we're really excited about that. And then I just have some cool eye candy, and I'll try and get through this and then answer questions if folks have questions. So this is some more integration pictures of FireSat, the first FireSat before we launched it in our facility in Mountain View. It's a little bit hard to see, but the red piece kind of tucked in the back is covering the aperture of the fire instrument. A lot of the rest of the stuff on here is antennas and the solar arrays before deployment. This is a picture, a little bit more of a close-up of the actual camera on that satellite and the satellites that will come later. And again, this is something that was critical to enabling the mission that did not exist in the world, and so we had to take on at Muon developing this instrument as well as a satellite. This is just a cool picture of our solar array deployment testing before we actually sent it to space. And then I have some data, and so this is some of the earliest data. We released this publicly about a month ago from that first satellite. And, aside from the fact that there's all kinds of cool things you can see in this thermal infrared data, things like the fact that the runway in Sydney is warmer than the bay, and that you can actually see gradations in the temperature of the bay. The more exciting stuff is really when we started taking pictures of fire. And so this is a fire in Australia, a bushfire that we captured early on. And I unfortunately don't have a good comparison with some of the existing satellite systems, but you can probably imagine from that simulation what they would look like. And what we're seeing is incredible fidelity and sort of the resolution, the sensitivity to very small patches burning. If you look carefully in these images, you can see these very small, cool spots very clearly in the data, which is very important for fire managers making decisions. And you can also see, how we very carefully selected a few of the spectral bands for this mission with fire in mind, and so fire shows up very prominently, specifically in this kind of blue-green picture, which is the mid-wave infrared band. We also got lucky and caught some very small fires. So this was a really exciting kind of demonstration of just how capable this system is. This was a small roadside fire in Oregon, and we actually got pictures from the local responders that responded to this, and we think this was about a 1/4 acre fire, very, very small. We caught it right after it started when we flew over. And the interesting thing about this is there was 911 reports and the first responders went out and put out the fire. But there's a set of other satellite systems, the civil systems, and then a set of other ones that are not discussed often that we're fairly certain nobody else saw this fire. So it's a very good demonstration of just how this, focus on really optimizing a mission for a particular use case can develop something that is very powerful for that use case. And that's my talk. I hopefully went through that fast enough. And if there's time, I can take a few questions. Any questions? Yes.
Hello. Hi, Jonny. I'm Christopher. I'm a third year here at UC Berkeley studying electrical engineering and computer science. And my question to you is, since Muon's strength is in data, which industries do you see Muon injecting itself into? And then what are the plans to scale in those industries, like with data analytics for the consumers? And where do you see this going?
Yeah, I mean, we definitely have a lot of strength in data, and I think that comes in a few different forms. I mean, one is remote sensing, the collection of data. I think it's also in the movement of data. We've really architected our system in a way that's very good at moving bits around. And so, I mean, I think our primary focus today and for the foreseeable future is going to be on things like these high-performance remote sensing missions, communications missions, things where you're trying to collect either photons or bits and translate them and then move them around various places. In terms of industries, I mean, it's interesting right now. So our customers span, we have a bunch of commercial customers. We have Earth Fire Alliance is essentially a nonprofit customer, and then we also have government customers. On the commercial side, I think long-term, there's a huge untapped potential around remote sensing that just largely because of the barriers to entry has never really been crossed. And one way to think about this is, historically there's been a small number of types of data collected from space, things like visible imagery. Now there's commercially available radar imagery, things like that. And those have applicability to certain problems. If you want to, see where cars are, high-resolution visible imagery is good. There's certain things you can help with that data, like some of it's used for agriculture a little bit, but it's usually kind of a secondary thing. And so I think one of the problems historically with remote sensing particularly has been that because it's so hard and so expensive and takes so long to get satellites into space, you try and build things to solve the general problem. You try and build satellites that can collect some data that hopefully have 100 applications. And I think that's very hard to do, and it has often not borne out that really moves the needle very much in any one of those applications. Where I think we're entering a place now where the barriers of entry have come down enough where you can say, for this particular application, if I want to improve crop yields, what's the most important type of data that I could collect to do that, to help farmers do better planting or water management or whatever? And then you can it's affordable to go build a system dedicated to that, launch it, and operate it. And I think that's a really fundamental paradigm shift in terms of how you think about some of these remote sensing missions that we're now on the cusp of being able to do. So I don't know if I perfectly answered your question, but that's some thoughts about it.
Oh yeah, that was great. Thank you.
Other questions? Yeah.
Hello? I'm not going to say my name because I don't want to get in trouble. So given what's happening in government right now, where they're shutting down NOAA satellites despite the fact that it's still working, do you foresee a scenario where Muon's FireSat's constellation would be would be like the only constellation standing that can offer this kind of fire detection? And after this administration's over, like do you see this as being a dominant thing, or you know what I mean?
Yeah, no, it's a very good question. We've been thinking a lot about it. I mean, I think that I think there's a lot of different dimensions to the question. So one dimension is, historically the government has built these satellites basically for the public good, for things like weather forecasting, that seems like, at least for now, are starting to go away. can industry step in some way to fill that void? And I think there will be places where that is the case. I think FireSat is hopefully a good example of a place that industry and philanthropy and other things are stepping in. I think the other part of the question is sort of one of the problems with a lot of the systems that are now getting deprecated and shut down is they were developed in this paradigm of billion-dollar systems that take a decade plus to develop and deploy. And each new one, replacing one of those, is another billion-dollar project. And I think what a lot of the trends in space going on right now enable are more leverage of the commercial sector to help make this less of a huge burden for the government. So the government doesn't have to spend in increments of $1 billion. They can spend in increments of $5 million or $10 million to get what they need. And also just that the timelines, the rate of new technology injection to these systems can be much, much faster. And I think that'll, over time, completely change how we think about the paradigm of these type of satellites, the things like science and earth science and weather satellites, how they get built, how they get deployed. I think the government still has to have a part in that because there's some amount of that is public good and will never go away. But I also think there is some truth to the fact that the old model was somewhat broken and needs to get kind of repaired. So I don't know if I perfectly answered your question, but those are some thoughts. Yep.
Given that Muon Space is, a lot of it is the businesses like collecting data for customers, how do you see like artificial intelligence and cloud computing coming into play with your business?
Yeah, that's a great question. So I mean, one of the kind of core theses for when we started the company was actually that, you know, this was 4.5 years ago and the world's changed a lot since then, but you look at the things that were happening in AI and the common denominator is that you need massive amounts of data to train these models to go do useful things. And they're incredibly powerful, and we believe that they were going to get more and more powerful, which has absolutely been true in the time the company's been around. But if that's the case and these models go and replace a lot of other ways of doing things and solve a lot of problems that have previously not been solved, what's going to enable that one layer down is data, is the data that's powering the models themselves. And so we saw that as a huge opportunity. Again, it kind of goes back a little bit again to what could really unleash things like remote sensing data in the world. I think the trends in AI right now could really unleash that. And we're seeing this, for instance, I don't know how much y'all have followed this, but Google a month or so ago announced that they're training what they call these Earth Foundation models, which are basically taking large-scale remote sensing, largely satellite data, and building foundation models out of them that are really meant to solve general-purpose problems or questions in a unified way, rather than having a bunch of different bespoke models. And I think that as that trend continues, there's going to be a near insatiable appetite for not only more data, but different types of data. And many of those types of data are going to need to come from space.
Thank you.
Other questions? Cool. Thank you all.